So in the last section, we painstakingly went through the idea of getting a p-value after building a confidence interval for difference. So let's do a couple more examples in a shorter fashion and focus on the substantive interpretation. Because ultimately, in real life, the computer will do all this for you. I want you to know where it comes from and the ideas underlying it, but in real life, you'll have the aid of a computer. Here's an interesting example. Two different physicians assessed the number of palpable lymph nodes, that is, lymph nodes they could actually feel, in 65 randomly selected male sexual contacts of men with AIDS or AIDS-related condition. And this is based on an example of real data, and the references given below. Here is the mean number of lymph nodes detected by doctors on each of the 65 patients. Two doctors, Dr. 1 and Dr. 2. And then we'll give the average difference and standard deviation of the differences here. So Dr. 2, on average, detected almost 3 lymph nodes less than Dr. 1. And the standard deviation of their individual patient level differences in the number they detected was 2.8 lymph nodes. So let's create a 95% confidence interval for the mean difference in the mean number of lymph nodes for Dr. 2 compared to Dr. 1. If we go ahead and do this, after accounting for the sampling variability in our data, it suggests that the true difference between the two doctors was negative 3.5 to negative 2.1, rounding up, lymph nodes. So on average, Dr. 2 found anywhere from 2 to 3.5 lymph nodes less than Dr. 1. And this really isn't about Dr. 2 compared to Dr. 1. This is more about the reproducibility of this diagnostic technique. And this result suggests that when two different raters are given the same patient, even if accounting for the imperfection and using not every patient, but just a sample of 65, there appears to be a systematic difference in the average number of lymph nodes detected by the two doctors, the two raters, that cannot be attributed to random variation. If we frame this in the hypothesis testing framework and get a p-value to go along with our confidence interval, well, we set up our own null and alternatives. The null hypothesis would be that the true mean difference were both doctors to look at all men who had sex with men with AIDS or AIDS-related conditions, that the true mean difference in their number of lymph nodes found would be 0, versus the alternative that true difference is not 0. So again, we first start off by assuming the null is true, and then computing the distance and standard errors between our observed mean difference on the 65 patients, between the two raters, the two doctors, and 0. And if we do this, we actually get a sample result that was 7.8 standard errors below 0. Our distance measure was negative 7.8. Is that unusual? Is that far out? Far away? Well, we have to see where this falls on the sampling distribution of all possible mean differences based on random samples of 65 patients. Well, the theory tells us we've got a relatively large sample. This sampling distribution will be approximately normal. So the p-value is the probability of being 7.8 or more standard errors away from 0, either below, as we observed, or above, 7.8 or more above. We look in both directions under a standard normal curve. Certainly, without looking this up in any table, you know that this p-value is quite low, right? It's well less than 0.001. Why do you know that? Think back to the basic quantities you've memorized about the normal curve. But of course, we can get Stata to do all our heavy lifting for us by using the CII command. So here we say CII, there were 65 patients rated by each of the two doctors in terms of the palpable lymph nodes. The mean difference between the second rater and the first was negative 2.75, standard deviation of 2.83, and we're testing this against the null of 0. Here are our results. And you can see the confidence interval there is what we got by hand. And the p-value, the t-statistic, that distance measure, negative 7.8. And the p-value that Stata gives us, it just gives us 0.0000. It truncates this very small number at 4 decimal places. A p-value can never technically be 0, but it can be close to it. So I would advise you never to report a p-value of 0, but you could put p less than some arbitrary threshold, like I had in the last slide. P less than 0.001. So again, this is an interesting study, and the results, it's not so much about comparing Dr. 1 to Dr. 2 at this point, because there was no gold standard for assessing the possible infection status of such patients. And the goal of this study was to assess whether doctors looking for palpable lymph nodes would come to similar results. And this results of this study, based only on 2 doctors, suggest that that's not necessarily the case, that there appears to be a real potential systematic difference in the diagnoses in terms of number of lymph nodes on average done by different raters, using doctors 1 and 2 as an example of 2 different raters. Let's look at another one that made made a lot of news when it came out. Certainly Oatbran did, and this is one of many studies that made a case for Oatbran. This is about cereal, really about Oatbran and cholesterol. And it's a real study in which 14 males with high cholesterol were given Oatbran cereal as part of a diet for 2 weeks, and the rest of the diet was regulated as well. And then they were given cornflakes instead of Oatbran, but the same rest of the diet for another 2 weeks. And what the study wanted to do was compare at the end of each 2-week period, their LDL cholesterol levels were measured in each man, and wanted to compare whether there were any differences in those levels or not. So after the 2 weeks on the cornflake diets, the average LDL across the set of 14 men was 4.4 millimoles per deciliter, and the Oatbran, it was 4.08 millimoles per deciliter. So a difference of 0.36 millimoles per deciliter, cornflakes to Oatbran. So let's just use the data and the sample results to create a 95% confidence interval for the difference in mean LDL, cornflakes versus Oatbran. And if we do all this and go through the computations, which are near and dear to your heart by now, we take our sample mean difference, add and subtract a little more than 2 standard errors, because we actually need to appeal to a t-distribution with 13 degrees of freedom. And if we do all the math, we get a result in confidence interval for the true mean difference for all high cholesterol men on cornflakes versus Oatbran in this diet setup of 0.13 to 0.6 millimoles per deciliter. So in this situation, after accounting for sampling variability, there's a wide variability in that possibility for that difference at the population level, but all possibilities are positive. So if we wanted to turn this into a p-value as well, how would we do that? Well, we'd start by specifying our alternative and our null. The null, of course, that the true mean difference amongst all such men on the 2 different diets is 0, and the alternative being that it's not 0. And again, we start by assuming the null is true and computing the distance and standard errors between our observed mean difference and 0. And if we measure this all out, we get a result that was 3.3 standard errors above 0. So is that unusual or not? Well, technically speaking, we need to figure out where this falls on the sampling distribution of all possible mean differences based on all possible random samples of 14 patients, where we had 2 measurements on each, one on the cornflakes diet, one on the Oatbran diet. And the theory tells us that the sampling distribution is a t of 13 degrees of freedom. So the p-value is the probability of being 3.3 or more standard errors away from 0, either above, like what we observed, or below, to consider the extremes in the other direction. And we can look at this up in the table or go to Stata. And if we do our CII command here, see we get that same confidence interval we estimated by hand. The t-statistic is 3.3, or slightly, I rounded it to 3.3, but our distance measure is a little more than 3.3, and that gives a p-value of 0.005. So, again, our confidence interval does not include 0, and our resulting p-value is 0.005, which is less than 0.05, so using the standard cutoff level, we'd say we had a statistically significant association between Oatbran versus cornflakes and cholesterol. And so this is one of the studies purported to give evidence that Oatbran had some negative impact on harmful cholesterol levels. And the claim was made because of this statistically significant result, among other types of cholesterol level comparisons. By the way, in all these things, the direction of comparison is absolutely arbitrary. We didn't have to compare cornflakes to Oatbran. We could have done it in the opposite direction. Oatbran minus cornflakes. What do you think would have happened if we'd done that? Well, look at I just ran the t-test I. We would have, instead of getting a mean difference of 0.36, because the cholesterol level was on average 0.36 millimoles per liter, cornflakes compared to oat bran, we'd get a difference of negative 0.36, because the same story can be phrased as the cholesterol level was 0.36 millimoles per deciliter lower for those on oat bran compared to those on cornflakes. And we get a similar change in sign for the confidence interval endpoints, because all we're doing is it's the same comparison in the opposite direction. But the only things that will be impacted will be the sign of the comparison. Our distance measure is now negative, but our p-value is exactly the same. And this starts to give you one of the many reasons we consider extremes in both directions from zero, either 3.3 above or below, because by changing the direction of comparison, we get the opposite direction. So by considering both directions with every hypothesis test, we're sort of insulating ourselves against the arbitrariness of the direction we choose in impacting how we get a p-value. To summarize the first three sets of this lecture here, how do we do a paired t-test? Assuming we have paired data and can reduce our data from two samples of data to a single sample of differences between each of the pairs, we designate our null and alternating hypotheses. Usually the null is the true mean change is 0, or the true mean difference is 0, and the alternative is that this mean difference is not 0. We collect data. We go ahead and collect data. We compute the difference in the outcome for each paired set of observations. We compute the sample mean of the paired differences. We compute the sample standard deviation of the same differences. And then we go forth. We then compute a 95% or other level confidence interval for the true mean difference between the paired groups being compared. If we have a large n greater than 60, we take our sample mean plus or minus 2 estimated standard errors. If we have smaller n less than 60, we take our sample mean plus or minus slightly more than 2. Where we get that from is a t-table, or really the computer. And again, Stata will take care of the details for you. The point is we know what would happen under random sampling from sample to sample the same size without having to do it ourselves. So we're exploiting that machinery. And then to get p-values, what we do is we start by assuming that null is true, of no difference between the groups. We measure the distance of our sample result from the null mean, mu naught, but usually that mu naught is 0 in almost all cases. So the distance becomes taking our observed difference, mean difference, and dividing by the estimated standard errors. And then we compare this distance measure to the appropriate sampling distribution to get a p-value. And a reminder, what the p-value measures is how likely your sample mean difference, your sample result, as well as other results even less likely than yours are, how collectively likely these are if the null is true. It's basically a measure of your results, the likelihood of your results under the null. We're going to remind you of that at the start of the next section as well, and really get into what the p-value can and can't tell you. Just to remind you of what constitutes paired data situations, we'll go through the examples we did to remind you of the pairing. In example 1, we had the blood pressure oral contraceptive example, where we had a single group of women whose blood pressure was measured at 2 different time points and compared. So we computed the difference in blood pressures for each woman between the 2 time points, and that was our measure of comparison. Example 2, we had the degree of clinical treatment. Each patient received 2 assessments, so there was paired by patient 2 assessments from 2 different raters, 2 different doctors. In example 3, we gave the same group of men 2 different diets in 2 different time periods and compared their cholesterol levels at the end of each diet. Other situations that would warrant a paired data study would include a twin study, where each subject in sample 1 had their twin in the other sample, or a match case control scenario. Suppose we wish to compare levels of certain biomarker in patients with a given disease versus those without. So for each person with disease, we match them to somebody who was otherwise like them. These would be some examples of paired data situations.